So good morning. I am Krishna Kumar from Krishna's class. We consider the primary decomposition theorem, and in this lecture we give the proof of this. So one of the very interesting theorems which generalizes the diagonalization theorem as well as the triangulation. So this is the more general scenario that we are trying to do. Now we'll just note down the essentials of this theorem so that you would know exactly what we are doing. So we have now T belonging to NP. What we have is the minimal polynomial. Given by these are the PIs are distinct, PIs are distinct polynomials. So this is essentially the primary decomposition of P. You cannot reduce it any further. Now Ri are positive. Then we define Wi as one space of Pi T. That's a definition. Then what we have is that this is for I. Then we have the first statement is that V is the direct sum of each Wi is divided the third statement is that Pi is equal to P plus K. Then the minimal polynomial Pi This is the statement of the theorem. What we are going to do is to explore the proof of this theorem. Now we have already given a summary of certain facts that we will be using from the polynomial. So we will recall them at the right basis. So the strategy is essentially, or we take advantage of a theorem that is available to as well as in number theory, as well as in the polynomial. That is splitting 1 into the sum of polynomials associated with the minimal polynomials. Now this is the strategy of theorem. So we first take up the proof of theorem. First. Okay. Now what we want to do is to obtain projection operator. So see, this essentially allows us to have projections EI on WI. So EI becomes identity operator on WI and elsewhere it is going to be 0. That is how it is defined. Okay. Therefore, we get projections identity on WI and 0 on WJ. So we find polynomials such that HIT is equal to I on VI on WI and again use consistent notations in this VI. This is VI and this VI. HIT equal to I on WI and HI equal to 0 on WJ, J not J. So this requires H1 plus H2 so that this is the resolution of the identity. So how to get hold of such vectors? So how to Please be proceed. Take it. What we do is, for each I, define Fi product of J dot H. Now, F1, sorry, these two right pointers. And hence F1, F2, Fk are relatively that's quite easy to understand because each Fi will this Pi to the power Ri. So there is one factor missing from all this. I mean, you cannot have a common factor from all this. So that if you try to take something as a common factor, it will be easy in some of these. So it is relatively special. Now what one does is this. There exists, this is one of the theorems of polynomials G1 K such that sigma means one can be written as a combination of these relatively bright polynomials F1, F2, F5, Fk with coefficients Gi. So such Gi's exist, but this is one of the basic theorems from polynomial theory that we use. So this is an important existence of such things. So once you get that, these are going to be our H1, H2, etc. Okay. Therefore, we have set so that this particular relation is such. If you take Fi, Fj, note that whenever I is different from J is divisible by P. That's clear. Because from Fi, one factor is missing, but that factor is available in Fj whenever I is different from J and vice versa. Therefore, P divides Fi, Fj for all I different from J. Now we define which is essentially Fi T. They come so it is materially in which order. Then you see that what we immediately infer is that H1P that means you have that is P1 what more you have this property Fi Fj is divisible by P. So you take Hi Hj. Now Hi Hj is divisible by the minimal form. This is because for I not equal to, I mean this is true. For I not equal to. Therefore what you get? So we have zero. Consequently, we have I square. Quite simple, you take this sum and then multiply by Pi, so you get this property. Pi is out. These projections have been developed out of the transformation. Okay, it's been defined from T, and they are essentially. So we have seen the definition of PI. They are defined by as a polynomial. So each PI is a polynomial. PIs are projections which correspond to the direct decomposition. So we have got V1 plus V2 plus etc. Vk equal to I. So it's a decomposition. Now we ask what exactly is the spaces taken by. So we know that this is essentially the scenario where each or the main space of null space of so what we show is that, so we now show that main space of the P, right, where Wi is equal to the null space of it would be really profitable if you compare this with the diagonalization situation where you know that the PIT, because P becomes simply the product of P1, P2, etc. Pk, where PIs are all linear polynomials, and then see what you get. So this is a straightforward generalization of this research. Now we prove this. So we show that this is the one that we do. Okay. Suppose Then B is equal to projection of P. Since it is in the range of Pi, and Pi is identity operator on the range of Pi, therefore this is true. Hence, we have this is equal to and this is equal to Pi T to the power I Fi T now you see that what we have observed with some observation. Yeah. Look at this part. This we claim that this part is 0. Why it is 0? Because you see that Pi T to the power or P divides this. That's it. That's what this is equal to. That's quite simple. Let's take this, go back to the definition of FIP and CYP. So that implies projection of range of Pi is so what we have proved is Pi T to the power Ri B equal to 0. With the assumptions, after the assumption that we have so far. Therefore, this is essentially the null space of Pi T to the power Ri is given, is called the W. Therefore, this is. So we have proved one point. Now, what is to be proved is the other part. So that is good. Do the reverse equation. So let us start with W. Suppose then what you have is that V belongs to null space of PI3 this is it. If I is not equal to J, then we have a find Gj is divisible by so if it is not there in this, then it is comes from the other one. Therefore, what do you get? This implies already V is in the null space of this. That means Pi T R I V equal to 0. Therefore, we immediately infer before. Equal to 0. That is, you have changes. So Fj Gj will be equal to 0. Now that means Ej this implies I because we have assumed V belonging to the V1. Plus this property that we have got W1 plus Wk equal to V itself. So P1 plus P2 plus etc. Pkv equal to IV that is equal to V. Therefore, you see that Pjv is equal to 0 as long as V belongs to Wi, but you get P and V. What we proved earlier follows that completes the proof of work. What you have is I equals B. So that completes the proof of the first part. You compare with the proof of the diagonalization. Now we want to prove the second statement is that this is the statement. Now you start with this W belonging to the then you know that Pi is the power Ri of W I. So you have Pi t to the power Ri because they commute, I can just use this Wi which is equal to 0. But this part is 0, therefore this is 0. Therefore what does it do? This is that. So that is a very simple. Okay, now we go to the third part. The third part is talking about the restrictions of T to W. That is this T. The restrictions of T to Ti is of T to Wi is denoted by Ti. Then the minimal polynomial for Ti is Ti to the power. Third part. So we prove the third part. So let Pi denote T restricted. Then what you have is that Pi the power Ri. This is because you have all wi. That's it. Now this implies the minimal polynomial for Pi divides Pi the power. This is an annihilating polynomial for all wi. Therefore, the minimal polynomial should naturally be zero. So that's it. Now we want to prove that essentially the minimal polynomial is this. At least we know that the minimal polynomial divides Pi to the power half. Now let G be any polynomial such that GPI, that means G is an annihilating polynomial. Then we have GT into G this is because we have GTWI equal to 0 for WI belonging to I. And that implies GT of Pi and that implies now that in turn implies that GT of FIT vanishes, but otherwise this is not going to be, since reciprocal, which implies GFI is divisible by the linear polynomial is EI GFI, which implies yes, the linear polynomial from EI for EI is EI. So that completes the proof. It heavily banks on the properties of the polynomial spaces, especially the splitting of the identity or the splitting of one as a sum of polynomials is the feature. It allows us all these things nicely. Now it is once again look at that particular property, compare it with what happens in the case of properties of numbers. Before we can know the problems there, okay. Now we did the corollary. Let protections associated with it. The primary decomposition. The minimal polynomial. Then each EI this we have got in the light of the proof of the primary decomposition here. Get the definition of this. Yes. further, if S commutes just A is a polynomial in and S commutes with T. So you can easily show that S commutes with each here. In fact, S commutes with every polynomial in T. And in particular with subspace is invariant. Because commuting E commutes with S, it follows that S is the range space of T is invariant under S. That we have to do. That's a simple concept. So this is something one is like how these are. Just a few minutes. That's a very simple problem. Now what we do is we return back to the situation where the minimal polynomial is the product of linear difference. So at this stage, that's a situation that we are. When does it happen? Now this is the case. This is the case when algebra this is only a necessary condition. It's not a sufficient condition. This can happen even when f is not of we have already seen examples of this, that on R3 over R, we have the minimal polynomial splitting into product of linear factors. Okay? I didn't say that this splits into product of distinct linear factors. Never. There are situations where this is. We have been discussing it far too often, and I think immediately we know. Now let us see what the theorem that we have proved, primary decomposition theorem, proved, tells about this scenario. It's very interesting how the operator breaks up into certain special class of operators. After all, our objective is this: the given operator is broken up into what we call transparent operators. That's the whole purpose of this kind of theorem. So this is the theorem that we have proved. The primary decomposition theorem that we have proved is the generalization of spectrum theorem that we have proved. So let us assume I is EL lambda so that your P is of the form where this is 0 down. Characteristic polynomial. Now you see that this kind of breakup will happen when the field is algebraically closed. For instance, in C, every polynomial splits into linear factors. And we also have the theorem that given an f, there exists a algebraically closed field in which f is embedded. So these kind of properties that we have are there. Okay. Therefore, you see that it's possible to have this kind of scenario. Now let us see what happens in this case. So what is our? We just go to the notation. So our EI is equal to WI is the null space of P minus lambda I over I. Then PI is then what we have is this. This is what we call. Now what you have is the following. Let us define D to be equal to there is an operator. It's a linear combination. Now this certainly belongs to N. D fixed diagonals. Because in the case of D, you can easily see that this actually the eigenvalues are all lambda 1, lambda 2, etc. lambda 2. And you would have the null space of P1, P2, P3 making up this sort of whole space. So you have W1 plus W2 etc. W V. That's what we have. V is the range. This is essentially this. What do you have? You have V equal to then you have I equal to what you have is this, that is E is equal to E1 where EI is equal to EI. This is the scenario that you do. Now what you do is, instead of this, we replace it by lambda I PM. Okay. So that is your D. So D is essentially some part from. Now you take out from this D. So what do you get? Let us define by N this part. Now that's equal to so what you have is P is now broken up into an operator N plus or E. We have filtered out a diagonalizable path from P and we have left the leftover is given purpose. Now let us start working on this. The powers of this. Then n square is equal to square root. Use the fact that Pi Pj equal to 0 whenever I is different from j. Then this is what you get. This is equal to P minus lambda 1 I. And so on. what are the powers of this? N to the power r equal to suppose r is greater than or equal to rk. You can choose the maximum of r1, r2, etc. rk which are really equal to constants. Minus lambda I to the power r. This is equal to 0, this is 0. In fact, which implies n to the power r plus on each one of B. Right, look at this. B minus lambda I to the power r equal to 0. Now, so the leftover part, what is that? D is written as the diagonal part plus the operator n, and this is the leftover part. So D minus D is equal to n, and n has the property that n to the power r equal to 0. Such operators are called Nilpotent. That means if you take the powers of this from some stage onwards, the power is going to be 0. So you see n to the power r equal to 0 means n to the power r plus 1 is 0 for all higher values of k or n to the power say m, n to the power m is 0 as long as m is greater than. So from some stage onwards, it is going to be the powers would be identities. So such operators are called Nilpotent. What do you mean? such that now we shall make an observation. Take an example. Let A be equal one can easily show that A square this is very simple to do. In fact, you can say that if you see, one of the interesting features is that you see you have non-zero integers. Now what happens is when you square it, you see that the square portion will that is when you take A square is of the form 0, 0, the whole thing shifts. And now if you take A cube, it will turn out to be this is what it is. So the effect is that you take the diagonal elements 0, make it upper triangular, and maybe these elements are not equal to 0, then you see that this is an example of this formula. So, or generally, A given by this is the effect of squaring this is it shifts by 1 step. The effects of further multiplying with A is that it shifts it's not 0 elements or more elements 0 start appearing here, and then in the next stage 0 will start appearing here, and so it's finally 0. So that's an example. Another example is this. Consider the differentiation. So d of that is a linear operator. Well, you see that so what happens is that if you take b square, then it's a polynomial of degree n minus c. If you take e to the power n, it's a polynomial of degree n minus m. If n is less than, so you clearly see that d becomes nilpotent. Okay. So this is a nilpotent. These are two examples of nilpotent. So there are many operators which are nilpotent and you want to study because they take a fairly simple form. In fact, you see that all nilpotent operators can be reduced to this particular form. Now this is something that we are trying to, because this becomes what are called the proper types of nilpotent. So that's what we are trying. So let me stop here. Make a comment. What we can do the breakup process. This is the result that we take up in our next lecture. Thank you very much.